We are going over, by the way, you guys can, just in case the link will not work, we don't know, you can always record these lectures on your own as well. Um, we are going to go over chapter 2. Chapter 2 is Chemistry Comes Alive. So as the name of it implies, it's a lot of chemistry involved. All right. We will take a look at some of the basic chemistry, then we'll go into the biochemistry, and then we go from there. Interestingly enough, the matter, anything that has mass and take up a space is known as matter. Right? A state of matter is important. You could have a solid, liquid, or gas. In terms of the solid, has a definite shape and a volume. So think about an object that is solid, say your cell phone next to you. All right, it has a certain shape to it. It has a certain volume, which made out of a lot of electronics within, and so on. And the liquid has a definite volume and changeable shape. So if you have a water bottle next to you, you know, it holds a certain amount of volume. Say, for example, my water bottle, it's 500 milliliter, it says, all right? And it has a cylindrical shape because it's inside of those water bottle arrowhead. But if I dump that into a bowl, then I'm going to get like a half of a sphere. So you can see how the shape is changing. Gas, however, it has both shape and volume can be changeable. So you could compress the gas, you could expand the gas, and if you put it into any container with a particular shape, it's going to look like that as well. All right. So those are the state of matter. All right. Um, Next up, we're going to go ahead and take a look at the energy. Uh, Capacity to do work is known as energy. There are a lot of different type of energy, but we will discuss mostly kinetic versus potential energy. Kinetic energy is the energy in motion, energy in action. All right. Potential energy is energy of position or a stored energy. All right. A stored energy. Sometimes because you're changing your position, you're building up a potential energy. Think about bow and arrow. Here is your bow and here is the arrow. Okay. Now, if you pull on this string and, you pull it, for example, this is the string and you're pulling it and this is your bow now and here's your arrow. All right. Once you let go of that, the arrow is going to go forward, right? So here is your string again, and now a little bit later time, the arrow is going forward, all right? And therefore, you can see you build up a potential energy. That's potential energy. As you pulled the string back, you change the position, right? You're storing energy. There are potential energy all around us. There are potential energy when you ride your bicycle on top of the hill. Here's the hill, here's your bicycle, all right? And you going on top of the hill. You changing the position, now you store the energy. Now you don't need to paddle to come back down, all right? You see, in here, you're building up a potential energy. You let go, it's going forward now. So the kinetic energy is actually energy in motion, energy in action. So in this case, it is the kinetic energy that is allowing this arrow to go forward. It is the kinetic energy that is allowing your bicycle to go forward. But building up a potential energy is another thing. So potential energy can be built up and it could, both of them can be used. In other words, the driving factor for the kinetic energy could be a potential energy, all right? You might say, okay, how is this related to the physiology? Well, we do the same thing. As you eat, earlier in the previous lecture, I told you guys that as we eat, you're getting a lot of sugar and things in that nature and so on. So those are your fuel, all right? There are chemical bonds in the molecules that can have potential energy. As your digestive system and a lot of chemical reaction break them, you release energy, and those energy could be usable. It could be usable to contract your muscles. and again, producing kinetic energy, all right? Or it could be used to do other tasks for the cell, all right? But we're not going to concentrate that much, but there are other form of energy as well. For example, there is uh, chemical energy, electrical energy, mechanical energy, radiant or electromagnetic energy, nuclear energies, and so on. So there are so many other type of energy. And I briefly talked to you about these type of energy. All right. But again, the idea is that there are always different form of energy. Energy is important because in order for us to do the task that we do every day requires energy for even our cells to do the function in which they require energy. So we will learn more about those as well. All right, let's go ahead and take a look at uh, energy conversion. Energy always can be converted from one form to another. All right. You might have heard about the laws of thermodynamics. Energy cannot be created nor destroyed. Well, what happens to the energy? One form goes to another form. All right. So if you turn on your light, for example, all right, you got electrical energy. You know, your outlet, your light switch, as you turning it on, that's electrical energy that Edison brings it to your home, right? So electrical energy is going to transfer or convert to the light energy. The light energy is what is shining on you right now, all right? So one form of energy transfer or converted to another form. However, don't do this, but if you reach out and touch that light bulb, you notice that it's pretty hot, all right? This conversion of one form of energy to another is never 100%, all right? Really depends on what type of a light bulb do you have. Do you have a LED? Do you have, fluorescent light? Do you have, uh, depends, all right? So uh, it's kind of like a money currency. Sometimes if you have a dollar, you go to another country, they give you a certain amount of currency for that particular dollar and such. All right. In some countries, they might give you a lot more. Some countries, they might give you less. Some countries, they might give you similar. All right. Like Canada, for example. All right. So, uh, but anytime you go to the bank and you wanted to, you know, convert your dollar to, let's say, another type of currency, say yen or pesos or whatever, all right, the bank might take something out, all right? They call it currency exchange rate. I don't know what the percentage might be, but each bank may have different percentage. They take out something. So you're never going to get 100% what it's worth. If the market for the dollar, let's say, is this much, you're not going to get exactly that much. You're going to get less because they take out some in between to make money. All right. Same thing in here. All right. We're not going to get all of the energy that is in the electricity to get the light. That would be great if we could have done that. But heat is always lost. Heat is not, for our explanation, heat is not a good source of usable energy. And in our system, it's the same thing as well. When you're eating glucose, the glucose is a fuel. You break it down in glycolysis or breaking things down. All right, you're not gonna get the 100% either. You're gonna get perhaps some. Our system are more efficient. A living system is more efficient than a non-living system. For example, if you compare your body with a car, your car needs a gasoline. Yes, you could convert the gasoline or the chemical energy in the gasoline to the combustion reaction and mechanical energy that allows you to go forward. But again, if you touch the engine, it will be super hot and you're losing a lot of heat from there. So depends on your how many miles per gallon you could get. You know, your energy conversion might be different, but there's always energy lost in between. All right, moving right along, let's go ahead and take a look at the composition of matter. Elements are unique substances that cannot be broken down whenever you're doing a chemical reactions or whatnot. When we get to the element, that's it. It cannot be broken down anymore. So usually this is referred to the building blocks of the element, which is known as atom. Atom comes in with different symbol. All right, usually one or two letter used in order to indicate what is the atomic symbol. All right, like for example, H is for hydrogen, but sometimes we use two letter. He, for example, is for helium because H number one is already used. Helium is number two in the periodic table, so we use a second letter and so on. C is for carbon, for example. All right, but Ca is for calcium. All right, so you get to see few of these chemical letters. So you know, you could get used to it. Sodium, for example, potassium, chloride, for example, iron, for example. You know, so we will take a look at some of them. All right, nitrogen, for example. In fact, hydrogen, nitrogen, carbon, and oxygen, making up about 96% of our body mass. So if you want to, you could text your friend and say you're nothing but oxygen, carbon, nitrogen, and hydrogen. You probably be correct. All right. So he might think you are on some kind of a drug, maybe, I don't know. But, you know, this is true. All right. So we can go ahead and take a look at the properties of element now. Each of the properties in the periodic table, they have certain properties. These properties could be physical properties that we can detect by senses. In other words, what do they look like? How does it taste? How does it feel, etc.? What do they smell like? And the chemical properties is how do they behave, all right? If we put them together in the chemical sense, are they reactive? Are they you know, form a bond with one another, or they repel one another, they attract one another, etc. So this is where it becomes important how molecules are being formed and how the molecules are being broken down, which we will talk about later. All right, moving right along. Next up, we want to go ahead and take a look at, as I mentioned to you earlier, these are called major elements because about 96% of our body mass is comprised of these four elements. All right. So, what about the rest? What about the other 4%? Where is that 4% coming from? What is it, and what we should know about? Okay, so let's go ahead and take a look at the rest, see what they are. So there is also what's known as a lesser element, which is again 3.9%. And many of these will come back later and take a look at it. Calcium, phosphorus, which happen to be plenty of them in the bone, potassium, sulfur, sodium, chlorine, Cl. You know, there's a lot of ions in our blood, including sodium, including chlorine, including potassium, including calcium. You mentioned that, right? Magnesium, Mg, all right? And iodine, iron, it's happened to be in the hemoglobin, all right? You might have heard about iodine salt, all right, to prevent goiter and all that. All right, so trace element, you could find it very, very minute amount, not a whole lot, like zinc, for example, all right? Zinc is a trace element, all right? Uh, Manganese, you know, those type of things. Now, what if there are elements that they're not supposed to be in our body, but they are? We cannot count those as the elements of the human body because they probably enter through our environment. They're not part of our body, right? Some of those elements like aluminum, right? We're not made out of metals. So what is the aluminum doing in our brain causing, let's say, in some patients, Alzheimer's, all right? Well, uh, you know, you need to educate yourself and try not to use a lot of products that have aluminum in it. A lot of medications have aluminum in it, all right? Antifungal cream, they have aluminum in it. Deodorants, they have aluminum in it, all right, to prevent, sweating and all that, all right? So make sure that all the products that you take, there's no aluminum because it could go right into your skin, into the blood vessels, and then it could kind of like get into different places and all that, all right? Lead is another one. Lead poisoning, lead-based paint, a lot of old structures, they have lead in the paint. They used to have that. And sometimes, child, they put everything in their mouth, including some of the paint that is chipping off. So again, the idea is that, those elements, yes, they can come into the body, but they're not belong to the body. Hg, mercury is another one, doesn't belong to the body, so I shouldn't put it here. All right, so let's put it up here. Uh, Hg is for mercury. Mercury, again, we're not supposed to have it. Then why is it that when you analyze the certain patients, they have high level of mercury? Maybe because they took, a lot of fish. Sometimes the fish, they eat the mercury through the ocean because of the contamination, and companies, illegally they dump their waste, unfortunately, in the ocean, and it's hard to enforce everybody. A lot of countries do that, right? They put all the junks in the ocean because they don't want it to, you know, they don't want it to, they don't know how to, and it's costs, to put them in the container, make sure, uh, they are safe and everything. So just because of the money to save, they just do all kinds of things. All right. And sometimes people, they just doing the wrong things. They don't care. It's unfortunate because planet belongs to everybody. But, time and time and time, there are individuals that they do not care about anything. All right. So that's my opinion. It's a good idea to always be a good citizen and care about your community, care about what's happening around you, your environment, things in that nature. All right. Uh, Even though you may not get caught, but if you do something, you're ending up hurting yourself. Pesticides is another thing. There's a lot of organophosphates in the field, and people putting all kinds of pesticides because they want their lawn to be nice and free of perhaps weeds. And some of this stuff, as the rain comes in, these pesticides moves. They go to their garden, they grow their vegetables and so on. And they're thinking, oh my God, look, I'm growing my own vegetables. Isn't that great? And they eat that, but they're actually, the roots capture all that poisonous stuff that you're applying. And again, come back to haunt you. So some people don't care, and some people, they don't know what they're doing. All right. The atomic structure. Atoms are made out of neutrons, protons, and electrons. When we're talking about these, electrons have a negative charge, proton has a positive charge, and neutron have no charge. In terms of the mass, how much they weigh and so on, neutrons, they are what's known as one atomic mass unit or one AMU. Proton is one AMU, and electron, we think of it as very negligible. It's not that much. So 0 AMU, that's fine, but they actually have, uh, you know, a, a little bit of mass, but not a whole lot. So the neutron and the protons usually towards the center of that element's atom, and the electron, they are running in the orbit around them. All right. So Let's go ahead and take a look at an example of that. Right over here is a helium. So helium, we can put He. That's their abbreviation. In this case, it has two protons. Protons are in red, so there's two protons. There's also two neutrons. Neutrons are in yellow. All right, so this is in the center. This is a nucleus. We're talking about atom. This has nothing to do with the cell. I know some of you guys took anatomy and they're thinking, oh, nucleus, I know where that is. That has nothing to do with the cell nucleus. Nucleus, it just means towards the center. All right, so the majority of the mass is right here. So if we know what amount of protons do we have, how many neutrons we have, we could just add them up, and you could easily know the uh, atomic weight for it. Atomic weight for it in this case is 4, because 2 plus 2, it has 2 protons and 2 neutrons, and there you have it. All right, and the electron, we said, doesn't have that much mass, so we don't looking at it, but it has 2 electrons, and in this case they're putting it outside. Sometimes they use it as a electron cloud, because at one time we don't know where it is. It's just orbiting really fast around the nucleus and so on. They're just like rotating, so that's what it is, electron. Now, a lot of times we didn't put anything on here. Sometimes you might see something like Na plus or chloride negative. How come we're not putting anything in here? The reason is this, because the number of protons and number of electrons are the same in this case. If they are the same, then the charges would be the same. So there's no point putting it, all right? So in this case, you have two positive, two protons. Protons are positive, and you have two electrons, two negative. Negative and positive, they neutralize one another. So there is no charge in here for the helium. That is not the case on the sodium, all right? Sodium has one extra proton compared to the electron, all right? That's why it's positive 1. Now, if it's more than that, sometimes you put positive 2, because it has 2 more protons than the electron. And the chloride is negatively charged, so it has 1 extra electron in this case, all right? So let's go ahead and take a look at atomic number. Atomic number is always the same as the number of the proton. Can you guys, just on a sheet of paper, what do you think is the atomic number for the helium? All right, the atomic number for helium, all right, is, you could pause the video if I give it to you a little bit later on and see if you could figure out, is the same as the number of protons, which would be 2 in this case. All right, so what about the mass number? Mass number sometimes is atomic weight. If they're all the same mass, is the same thing, but it's a little bit, you consider the isotopes. I'm going to talk about it later. Mass number is the number of electron, number of neutron plus number of the proton. So this number of neutron plus number of the protons is giving me the mass number. So in previous example for helium, we had 2 neutron, we had 2 proton, so we have 4. Mass number is 4 AMU, atomic mass unit. Atomic number was 2. All right. Now, let me go ahead and pause the video. All right. So in this example, yes, a mass number would be 7, and atomic number would be 3. That would be for lithium. All right. Good job. Let's go ahead and take a look at a few other things. Molecules and compounds, when you have 2 or more atoms, colliding with one another and they get stuck to one another, this is called a molecule. All right. Let's say hydrogen and hydrogen collide with one another. Now you get the hydrogen gas. Oxygen and another oxygen, they collide with one another. Now you have oxygen molecule. All right. However, when we talk about the compound, or sometimes also known as a compound molecule, is whenever you have many different kinds of atoms. They're not necessarily the same, all right? For example, you got H2O. This is considered as a molecule still, but it's a compound molecule because all oxygen and hydrogen, they are different, all right? Next up, we would wanted to talk a little bit about mixture and the solution. Mixtures are substances composed of two or more components, physically intermixed. All right. Most matter in nature exists in the form of mixture, but there are only three basic types. you know the basic type is solution, like for example, you have a solution uh, of let's say mineral water. All right, mineral water is a solution of water and some other mineral in it. All right, or it could be colloid. Colloid are the solute particles are larger than the in the solution and scattered light. All right. For example, think of the Jello. All right. Jello is a good example of colloid. All right. And then you have a suspension. Suspension solute particles are very large and they kind of like settle out. One example of that mixture would be suspension. So mixture can be solution, mixture can be colloid, mixture can be suspension. Suspension, like, when you suspend the blood sample, if you have a blood sample, what happened? All the heavy stuff will go, like larger stuff goes at the bottom, right? Red blood cells and so on. So you get like all these cells in here. And then on top part, we call this plasma, which is mostly lighter stuff like waters and things like that, ions and things like that. So this is suspension, all right? Uh, Colloid is like jello, and solution, I just told you, like mineral water. All right. So solution, again, it could be gases, liquid. There are many different type of solution, but most of the time, what we're going to be looking at, you need to know what is solvent and what is solute. Solute is the substance that are being dissolved. Solvent is the substance that are doing the dissolving. Yeah. So what that means is this: when you have, let's say, glucose in the blood, all right, the blood obviously has a lot of water in it, so that would be your solvent, but the glucose inside of it is the solute. All right, that's the idea. All right, so let's go ahead and take a look at the next one and see if we can get the idea. Um, uh, Chemical bonds and the octet rule and valence shell and all that. So again, at the beginning, it might be a little bit new to you, especially if you haven't had chemistry for a while. This might be intimidating. Give yourself a little bit time, and I'll try to make it as basic as possible. As basic as possible. All right. So electron shells and energy level. What is the electron shell or energy level? This is the pertain to the electrons around the nucleus that we discussed. All right, but they're coming into a different energy level. So uh, bonds usually form only on the outermost energy level. So for our purpose, again, there are many different energy level, but for our purpose, think about that you have certain atom. We don't care what that is right now, all right? But the first energy level can have up to only 2 electrons. Well, you might say, what about hydrogen has only 1 electron? right? Uh, then you just fill in one, and this atom becomes hydrogen, right? But helium has two electrons, so now it's helium, has two electrons. You see, right? So this is the first energy level, all right? Earlier, we mentioned that, look, this is two, this is one. Lithium has three. Notice that they put this one outside. Now, this is the one that can participate in the chemical reaction. Electrons on the outermost energy. However, if the energy level is completely filled, like this one is completely filled, then they are not that much reactive. All right, this is called inert or noble gases and things like that. All right, so we're going to go ahead and take a look at the other energy levels so you get a feel for it. All right, so after the first energy level, you can have two electrons on the first energy level. After that, you can have up to 8 electrons in the second energy level. That is only if you have enough electron. If it's hydrogen, just one, then you just put in one right here. All right, you start off from the inner one. This is the outer, this is second energy level. Now, if you have even more than that, you're going to go to the third energy level. That's the third energy level. Third energy level, you could have up to 8 electrons as well. Yeah. All right. So we have to fill them in. First, go to the first energy level. Then you go to the second. Then if you even have more, you go to the third. And that's as far as we're going to go. There are more and it gets complicated, but that's how it is. All right. So let's just say, for example, sodium has 11 electrons. All right. See if you can put these 11 electrons in here. Fill this up. So I have to fill this up first. Two of them is done. I got 9 more, right? I got 9 more. Okay. No, yeah. So the next one I have to put in here. The second energy level takes up 8. So if I put in 8 electron in here, so far I used up 10. I have one more. So the next one I have to put it outside right here. This is called the outermost electron. All right, outermost energy level or valence shell. All right, that's what it's called. Okay, so this is an octet rule of 8. In other words, that's the key to understanding how the electrons are behaving. But in a very concise way of seeing these things is kind of like a roller coaster, huh? If you go to the roller coaster, right now everywhere is closed, but let's say, I don't know, maybe they're open. Here's a roller coaster cart, okay, in Magic Mountain or something. People are standing in line. Now there are 6 feet of water, maybe, I don't know. Anyways, the first cart is going to take only 2 persons. All right. What if there are more people in here? The third person cannot go sit in here. There's only 2 chairs in there. Has to go on this one. On this one, there is 8 chairs. Okay. So there are 8 more. They can sit in here. But right now, it's only 1. In case of the sodium, for example, if these are being like analogous to the electron, this would be like a lithium, right? But if you have more, then you got to fill this card first, which is up to 8, then go to this card. All right. What if the first person says, "Oh, I don't want to sit in the front"? You cannot do that. That's it. That's first. You got to place the first person in there. All right. That's how it works. You don't want it, then don't come. Okay. All right. So this is how it works. Now let's go ahead and do a activity just for fun, you guys. Let me go ahead and erase this. And this is just a fun activity if you like. you could participate and think about yourself as an element, okay? And think about the month that you born as an electron. So if you were born in January, just putting, fill up the first shell and leave the other one empty. That's for January, okay? Now, if you are born in October, you need to go to the second energy level, for example. Okay, so really quickly, grab a sheet of paper and a pen. I'll give you time to do that, all right? And write, this is also known as an electron configuration, or write your energy levels and so on. Don't be upset if you have only one energy level. That's okay. Later on, I'm going to see, okay, this is me, for example. Okay, I wasn't born in January, by the way. Mine was May, but I don't want it to put it so that you see it. All right, I wanted you guys to think of it on your own. Then, if you have a partner, a wife, maybe brother, sister, boyfriend, girlfriend, whatever, uh, draw theirs too. Draw theirs too. Okay, this is me, for example. You write down your name and then, draw another one. If you don't have anybody, maybe you have a dog. I don't know. If you know when it was born, you could put theirs. Doesn't matter. We want to see if this person later on bonds or not, just for fun. All right. So go ahead. I'm going to give you guys a few minutes to do that, and we'll come back. All right. So let me pause the video. All right, so these are the inert elements when the outer energy level is completely full and therefore they are not reactive. Moving right along, these are reactive elements. Again, you make sure you understand this, that the lone electrons on the outer shell participate in a chemical reaction. That's very important. All right. So in this case, hydrogen can take up another electron. So it might collide with another element and they can perhaps, formulate a bond, which we're going to go ahead and take a look at it shortly. All right. Um, it really depends on the outer shell, how many electrons are there and how many, bonds they could have. Like the hydrogen, for example, you could have uh, another hydrogen, binding here. Sometimes when we put in this line, that means they are forming a bond in between. But I will cover and tell you guys how this happens. So for that, we need to take a look at three different type of bonds: ionic bonds, covalent bonds, and hydrogen bonds. Let's go ahead and take a look at each one. Ionic bonds occurs when you have uh, electrons transferred from one element to another. Then it forms the ionic bonds. Let's take a look. Let's take a look at the ionic bond. So the key is the transfer of electron from one element to another. If that happens, if you are getting the electron, this is called gaining of electron. If an element losing the electron because it's going somewhere else, that's called loss of electron. So this is how ion forms. There are two types of ions. One is called anions. A good example of it would be chloride negative and cations. Cations is like, anything that has positive on it. That's called cation. One way to remember is cation. Look at the T, it looks like positive. So you could easily associate it with the ions that are positively charged. All right. So what happens to this one? Gained an electron. What happened to this one? Lost the electron. Remember, electron was negatively charged. All right. So this is exactly what happens now. One is positive, the other one is negative. They can attract with one another, which is ionic bond. Ionic bonds are not really strong, they're weak. but there is an attraction going on. Now you have NaCl, for instance, all right? Because the positive and negative, now we don't show it because why? Because there is an attraction and they neutralize one another, but that's what happens, all right? Let's go ahead and take a look uh, at sodium chloride, which ionic bond forms between the two elements, and that is because of the transfer of electron. Right here, we earlier did the electron configuration of sodium, and we said there is only one electron goes outside, all right? So, and we said this can participate in a chemical reaction. In the chlorine atom, if you draw it, first energy level gets 2, that's this one. The second energy level gets up to 8. So 2 plus 8, 10. I still have 7 remaining. So the other 7, I have to put it on my third energy level. All right. Which again, it's one of them really needed badly in order to become stable. Because whenever the outer shell electrons are not completed, then it's not as stable. They want it to react. All right. So in this case, electron is lost from the sodium and the chlorine atom is gaining the electron, so it becomes chloride ion. So the positive and negative attract one another, and this attraction is called ionic bond. All right, which sodium chloride is another name for it, is the salt. That's what it is. All right, and the salt is uh, combination of sodium chloride, sodium chloride, sodium chloride. So there is a lot of attraction going on between them and so on. All right. So that is formation of the ionic bond. All right. Next up, we're going to go ahead and take a look at the covalent bonds. Covalent bonds forms when you have sharing of the electron. So the electrons is not going from one to another or getting transferred from one another. They're actually sharing. So electron sharing is important. All right. This produces molecule. And we can go ahead and take a look at an example of one so you'll see it a little bit better. All right. So let's go ahead and take a look at easy one first. Here is the hydrogen. As you remember, hydrogen had 1 electron, so we fill up 1, but the first energy level can have up to 2 electrons. But what if I have another hydrogen element nearby? All right, so you see what happens? This one is the same thing as well. But if they collide with one another, then what will happen is electron from this hydrogen, say the one on top, an electron from this hydrogen, say the one on the bottom, all right, they can share with one another. All right, it's supposed to be the same size, but it's not, that's okay. All right, so this is a sharing of the electron. So if I put my hand on top of this or take, you could place your hands on top. You cannot see me doing it right now, but if I put my hand on the top right here, usually I have the board in order to tell you. So this is my hand, for example. I cover this, right? You only see this one, and then the first energy level still has 2 electrons in it. And if I take my hands and put it back on the left side, again, I'm going to look at the hydrogen in the same manner. So if I go ahead and erase this and, put my hands on this one, it's still the first energy level can have up to 2 electrons, you see? All right, so these 2 electrons are being shared. One is from this hydrogen, another one is from this hydrogen, but they're being shared. And a lot of times sharing of the electron can actually be shown as a line, hydrogen and hydrogen, or you could just write it down as H2, all right? What that means is there is a covalent bonds. Covalent bonds means sharing of the electrons, all right? Now, let's go ahead and take a look at the carbon. By the way, carbon dating is really popular when you find a bone structure from dinosaurs or You wanted to find out, the specimen, how long is it from, and so on. They do carbon dating. They analyze the carbon. Carbon is very versatile atom because it can combine and covalently bond to many different other atoms. So in this case, you could see a hydrogen atom and you see a carbon atom. On the outer shell, you have only four. Here's one, here's two, here's three, here's four, but we can actually get up to eight. All right. So if there are hydrogen nearby, they could come in and again collide, and we could get methane gas, all right, which is carbon and four hydrogen. All right. So in this case, how many covalent bonds? All you have to do is just count the lines. Here's one, here's two, here's three, here's four. There are four covalent bonds. One of these, it would have been better if they had the different color, but one of these is for hydrogen. But again, if you put your hands on the hydrogen and if you count the outer shell electron, it still is going to be eight. Don't worry if they show it like a stuck in here. It really doesn't matter. You could put in carbon in here, and the first shell, there's two, and the second one, I'm just going to show you this side. You could put it like that, you know, and one of these belong to the hydrogen, you see, like that. I like it to draw it like this, to be honest with you, because it shows like one of these is from hydrogen. And even better, if you like, you could just color them, so it indicates that, one is for hydrogen, 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 hydrogen. But if you again put your hands on all the hydrogen and you count the second shell, it's eight, octet rule that we discussed, right? So you could easily figure that one out. Now, what I want you guys to do is go back to your own drawing. Remember, you had yours drawn and you had your friends or your loved one drawn. See if you can, form a covalent bond with one another. All right. So I'm going to pause the recording. All right. If you were able to, that would be great. If not, don't worry. You could work on it. And let's go ahead and introduce the double covalent bond. Double covalent bonds, instead of two electrons being shared, now you have total of four electrons being shared. Take a look at down here. There are four electrons are being shared. Two of them from one oxygen and two of them is from another oxygen. But together there are four electrons are being shared. So remember, the hydrogen and hydrogen, two electrons were in here. So if this one is four electrons right here, which we can count the circles, then we have double covalent bonds in here. So you have to put in two lines in there, okay? Double covalent bonds is stronger than the single covalent bond. And yet you have also triple covalent bonds where six electrons can be shared. All right, six electrons can be shared now. All right, uh, triple covalent bonds such as nitrogen gas, all right, N2 can form. And again, uh, you can go ahead and take a look at a double covalent bond, and you could compare it with triple covalent bonds. What you see is that the difference is they have one extra line. So six electrons are being shared in this case. Six electrons being shared. All right. Now, How many double covalent bonds do you think you have?
2. No.
1.
Okay, one. You have only one double covalent bond. All
Oh.
right. Now, how many single covalent bonds do you think you have?
8. 10.
Let's count it. Okay, here's one,
11.
2, 3,
10,
4, 5,
5, 6, 7,
8,
8,
9,
9,
10.
10.
All right, so we got 10 single covalent bond and one double covalent bond. All right, how many total covalent bonds do we have in our single? And now, do we count this as two or do we count it as one? So again, you could say, for example, 10 single covalent bonds and one double covalent bonds. That would be the best way to do it. Okay. All right. So you could see carbon is very versatile. It can combine with a lot of different things and so on. So anything that contains carbon, we call it organic. All right. So, and now that you have a little bit of understanding, again, these are a lot of chemistry. I'm not sure if what I'm covering and making sense to you or not, but we need to go forward. There is something known as a polar covalent bonds and non-polar covalent bonds. What does that mean by polar covalent bonds? Whenever we say polarity, that means there is an unequal sharing of electrons. Certain elements are known as electronegative. All right. Electronegative are those elements that they have 6 or 7 valence shell. What does that mean? That means outer shell electron, it's either 6 or 7. Then they will be electronegative. Well, what does that mean? Well, before we go on and talk about what does that mean, let's see if we can identify few of these. All right. So for that, we need to let's take a look. Do you see any electronegative elements in here?
Carbon.
Again, you must look at outer shell electron. That's called valence shell. Is any of these valence shell electron 6 or 7?
Oxygen.
Oxygen.
Okay, so if we go ahead and take a look at 1, 2, 3, 4, 5, 6. You're right. Oxygen is electronegative. Anything else? No.
No.
In this case, none of them are electronegative other than oxygen. All right. So valence shell. So what can we say oxygen is? We can say is electronegative. That's what we can say. So what? Why? How is that important? Electronegative elements, they pull the electron towards themselves. Why are they doing that? Because they want to get filled up. The whole energy level like to get filled up. So they're pulling the electron towards themselves. That's the idea. All right. So if you have an oxygen, for example, and you have a hydrogen, remember hydrogen had only one electron, and another hydrogen right here. All right. And here they're colliding with one another. They can share the electrons. So you got two covalent bonds in here, but the covalent bonds are not distributed equally. So if we wanted to kind of like draw this with only the electrons that are being shared, electrons are being shared are closer to the water, to the oxygen right here. All right, they're pulling these electrons toward themselves. When are they doing that? They're doing that because they are electronegative. Only electronegative do that. The more electronegativity, the more pulling they do. Imagine this might be a good analogy for you to think about. There is a, you know, there is a person that is taller, bigger, stronger than you are, for example, huh? And you're have a rope, all right? But this person keeps pulling the rope towards himself. Now he has more rope than you are, all right, than you have, all right? That is called electronegative because they have more power. The rope in this case is kind of like an electron. Now you're not letting go of the rope, but pretty soon he's going to have more side of the rope. So what does that do? Well, if the rope is electrons, then the oxygen part right over here is going to be a slightly negative because remember the electrons are being pulled, all right? Electrons, kind of like this rope. This guy has more rope, so more electrons towards it. That means a slightly negative. This side is going to be a slightly positive. So sometimes you put S plus, that means a slightly positive because the electrons not near them that much. All right. This is not a transfer of electron at all. This is not ionic bond at all. All right. So has nothing to do with that. All right. However, that's what it is. They are pulling the electrons towards themselves, and therefore they are more electronegative. All right. What it does, it creates a polarity. Now, one side of the molecules is slightly negative, another side is a slightly positive. All right. Therefore, we can say this is a polar molecule. And these are polar covalent bonds because they are not distributed equally. What if you have oxygen and oxygen? Oxygen, we mentioned that they are electronegative. Is this a polar covalent bond?
Non-polar.
Non-polar, because they have the same power. If this person that is pulling the rope is exactly has the same power as this person and so on, guess what? They have the same amount of rope because the force pulling, they cancel one another. So what happens then? They're sharing this rope equally with one another, and that's exactly what is happening. These are being shared equally. There are 4 electrons in here because it's a double bond, but they are being shared equally. So what that means is a non-polar. Non-polar meaning what? Meaning that the electrons are being shared equally. This is unequal sharing. Unequal sharing. The non-polar, the electrons are sharing equally. All right. So you might say, okay, one is polar, one is non-polar, so what? Okay. How is that important? Well, it's important because uh, solubility and how substances go inside of our cells and get out of our cells are really important. And to understand that, you need to know if substances are polar or non-polar. Let me go ahead and give you an example of that. So that way you have some idea what's going on and we can go from there. Say, for example, here is of our cell. Here is what cell. In anatomy, you learn that the cell is made out of phospholipid bilayer. So there is 2 layers in here, right? And again, in anatomy, you probably learned that there are mostly, lipid, which is non-polar, all right? So if you have oxygen, and carbon dioxide, by the way, is the same thing. Carbon dioxide looks like this. So they're pulling and they're canceling one another. So easily, carbon dioxide and oxygen, they could go in and out of the cell that way because they have the same construction as the, or solubility as the plasma membrane. So that's how breathing or cellular respiration can take place. And again, we can discuss the details of that a little bit later on when we get to respiratory or other system. All right. So the third type of bond is called a hydrogen bond. Hydrogen bonds are too weak, and but together they can be very strong if you consider everything. But when you're looking at a single hydrogen bond, is not that strong. All right. Many times you see it in the molecules that are polar, and they, like, we call it dipoles because one side is negative slightly, the other side was a positive slightly, and they attract with one another. And that is responsible for the surface tension, by the way. All right. So high surface tension on the bond on the water, right? Say, for example, this is the water. Certain insects, they can actually walk on top of the water, right? Water strider is a good example of that, because they have a surface tension. Water has a lot of different properties, but hydrogen bonds is very important. Uh, we can see a lot of hydrogen bonds in our body, water molecules bonding with one another. There is a hydrogen bonds in our DNA molecule. There are hydrogen bonds in many, many different areas, such as how the proteins are, uh, combining and so on. It looks like I need to pause. Thank you. All right, so this is hydrogen bonds, and it happens due to the electronegativity and the polarity of the molecule, and each single water molecule can combine with four other water molecules, and again, these can also combine with four other water molecules as well. So again, when you look at this, it's enormous amount of energy required for all these bonds to be broken. So this gives a water a really unique properties. Even though if it's really hot temperature, we're not going to lose a lot of water overnight, because again, it takes a lot of energy in order to break all these bonds. So this is called the hydrogen bond. So far, what did we cover? We covered ionic bond. We call it covalent, both polar and non-covalent bonds. And finally, we discussed the hydrogen bond. All right. So those are the three different bonds that we covered so far. The key for ionic was transfer of electron. Key for the covalent bond was the sharing of the electron. And the key for the hydrogen bond, you need to have hydrogen. Look, they all have hydrogen. All right. And also you have to have a polarity, polar molecule, and hydrogen that have attraction towards the negative side to it. All right. So, uh, you know, one time I'm going to share this with you. I asked this question. Identify, it was a quiz question. Identify the bond that, you know, uh, it happens via sharing of the electrons. Obviously, sharing of the electron was covalent bond, right? But the choices were, it was a multiple choice. It was A, hydrogen bond, B, ionic bond, C, covalent bonds, and D, just for the fun of it, I put James Bond. And guess what happened? Three people put in James Bond. I don't know why, and why they put James Bond, but I don't know. Sometimes I think some students are on something. I don't know on what. All right.
Professor, I'm sorry, can you please just repeat what you mentioned for the hydrogen bond? You mentioned that all the hydrogen bonds are needed in order for a polarity.
Hydrogen bonds on the polar molecule. Water is a polar molecule. Hydrogen bond is necessary because it's called hydrogen bond. Okay. Most of the time, hydrogen does not have that much power. So if you have another electronegative element, such as oxygen, it pulls the hydrogen, it pulls the electrons towards themselves. So this side becomes positive. So another side that is negative, it gets attracted. All right. So because it's hydrogen, then that is called the hydrogen bond.
So is any bond with hydrogen a hydrogen bond or only
No,
this kind?
no. I told you they have to have a polarity going on. Okay.
Okay.
So the hydrogen bond is common between the dipole molecules, such as water. All right. One side is a slightly negative, one side is a slightly positive. Anything that does not make sense to you, you guys need to do further reading. All right. So look that up, look over it, and so on until you understand. All right. I'll try my best to give you a little bit more information, but some of these might be a little bit too much to digest in one shot. That's why we're the outside coming in, and you need to kind of like get a little bit further information, look at the different examples. Hydrogen bonds are really important between the intramolecular bonds, bonds between the molecules, for example. This could be really related to the three-dimensional structure. This could be related to the structure of the protein we're going to get into, a structure of the DNA we're going to get into. So there are many examples of the hydrogen bonds, but the idea is that is responsible for the tendency of the water molecule in this case to cling together and form kind of like surface tension. All right, at least for right now, that's the example of it. All right, so water properties are many. High heat capacity absorbs and release a lot of heat before changing the temperature. This is essential, especially for aquatic organism, because if the temperature were drastically changed right away, that would not allow many of the coral reefs to live under the ocean. As you know, coral reefs play an important role in producing the oxygen and removing the carbon dioxide as well, along with a lot of other, organisms that live in the ocean. All right. Also, it has a high heat of vaporization. Like I said, the changing the state from liquid to gas requires enormous amount of heat. So ocean and the river, they don't disappear overnight. It might happen over many years, or depends on the temperature, obviously, but a lot of time doesn't happen. If you have a pool in your house, or you know somebody that has a pool, the water level might come down a little bit in the hot summer days, but you could fill it up. You're not going to see like, drastically in a couple of weeks, all of a sudden your water is gone, all right, because it takes a lot of energy. Like I said before, they are clinging into one another. Water is a very important polar solvent. As you know, our blood chemistry involves in water. Our cells are immersed in water. All right, our cells surrounded by the water. Our cells inside of it, there is a lot of water. So water is a great solvent for many things. All right, so it's medium for transportation. It has important role in reactivity. In other words, there is a hydrolysis, which means break with water. Substances that are too large, whatever these substances are, hydrolysis, water comes in and break these bonds. Later on, maybe we can elaborate on it. Or dehydration, water is lost and you can put in things together. So for example, if you have two items together, when the water is lost, what happens is you actually put things together, all right, which is in the second part I could talk about, all right. There is a cushioning of the water as well. So again, certain of body organs are cushioning. In other words, you know, as you know, your heart was in the serous membrane, and there were like a pericardium, if you remember, and around it was water. We call it serous fluid, which is mostly water. Even your brain surrounded by water. Again, we called it in anatomy cerebral spinal fluid, but again, they're cushioning, they're protecting, uh, and so on. If you tilt your head left and right, your brain is not going to be banging on the cranium and get damaged easily because there are all these water substances around it. All right. So it gives the brain also a buoyancy so they could go on top and so on as well. All right. If you didn't have the water, brain could have gotten damages so easily. All right, but that doesn't mean we're not going to get damages. As you know, concussion happens all the time. In NFL, people get concussion all the time because the impact is so severe that could cause the brain to get hit to other objects and so on. Next up, so water properties we discussed. Next up, we're going to go ahead and take a look at chemical reactions. All right. So chemical reaction occurs when chemical bonds are forming. Either they can break or they can form. All right. Really depends. If you're breaking certain things, we call it catabolic reaction. If you're making things, we call it anabolic reaction. All right. So usually we use what you start off with as reactant and what you end up with as a product. Now, uh, a lot of time, you use the plus sign when you're combining different things, and then the product would be on the other side of the arrow. That means this is what we're getting. This is what we are starting. All right. This is what we're starting. This is what we're getting. So the arrow is showing you like which way to go. All right, pattern of the chemical reaction. Pattern of chemical reaction is A plus B give you AB. AB give you A plus B. AB plus C give you AC plus B. So in this first one is a combination. You combining the A and a B, you're getting AB. This one is decomposition. Decomposition means they're broken down into a smaller component. It's opposite. You starting with the larger molecule, you're getting A plus B. All right. Hydrolysis would be a good example of decomposition, and dehydration would be a good example of combination reaction. An exchange reaction, B and C, it looks like exchange. See? Now you have AC plus B. All right. So what are some of the factors influencing the chemical reaction? One is temperature. The higher the temperature, usually chemical reaction proceed quicker. The particles move faster, all right? And they can collide with one another. Particle size is another. So the smaller the particle, the faster the chemical reaction would be. Concentration, when you have a lot of A's, for example, and a lot of B's, for example, and combine them together, you're going to get a lot of A and B, for instance, because chances for them to collide is a lot higher. When you have an enzyme, enzymes are biological catalysts, all right? Catalyst, or it's basically speed up the reaction, all right? If you have the enzyme, let's say you could break down the food pretty quickly. If you do not have that enzyme, you're not going to be able to break down that food as quickly. You might get a stomach ache or whatever, like lactose intolerance and so on. All right, we can elaborate more on the enzymes a little bit later on, but right now I wanted to just giving you an idea that these are speed up the reaction enzymes. All right. This finishing up a part 1 of chapter 2, and let me go ahead and pause for a moment.